with great pleasure that I am welcoming all of you to the second edition of the conference on recent advances in mathematics and related areas. As I said, this is the second edition. The first one held in November 2020 alongside of integrated MSc PhD program. And that was a conference which was actually very well received. And that's one main reason why we decided to make it into an annual edition of sorts. And this is the second edition. So yeah, so welcome all of you. And we have as our first speaker, Professor Samit Dasgupta. I would like to invite Kalyan to introduce this speaker.
Thanks a lot, Pranav. And again, hearty welcome and good morning, good evening to all of you. As Pranav pointed out that the first edition of the conference was in December 2020. And all of us know that was the situation outside, pandemic was in full swing. And, we just talked among each other and we thought there should be a conference. And then we were talking about what could be the topic. Then we said that, this is a general mathematics conference are very rare. Usually some thematic or some particular branch that has been chosen for a international conference. So here we thought that let's have a conference in mathematics and related topics. And then the response that we got was overwhelming. That particular conference in December 2020, which was inaugurated by the Honorable Chief Minister of this particular state, Sri Pinarayi Vijayan. And as Pranav pointed out, this signature program of KSOM, this integrated MSc PhD program, was also launched with that one. And that conference really infused a new life. And I would say that from there on, this 1.5 years, it just went on for us. We had 2 more conferences in between and many other programs. And now KSOM, Kerala School of Mathematics, is in the mathematical society of all over the world. So I'm really thankful to all the speakers of the first edition. And then we decided to continue, as Pranav said, the response, the feedback that we got from all the participants and the speakers to continue this one. And I'm sure that this will be continued as an annual conference, which will be bringing together mathematicians from most of the active branches and related things like computer science, like even in physics, string theory, and quantum computation and all other things. So which was there in the first edition. Even this edition will have quite a lot of variety. So I'm sure that all the participants and the young scholars, those who are here, will be benefited from this expert talks that we have. We have really, this edition also has eminent speakers and really very well established who have contributed immensely to their particular areas, the speakers that have really agreed, and we are so thankful to all of them. And our first speaker of this second edition of the conference is Professor Samit Dasgupta from Duke University. He is a very well-known mathematician in general, if I call it arithmetic algebraic geometry. And I'm really happy to have Samit with us this edition, and he is going to talk on a topic which will be these young people who are there, the Stark's conjecture and Gilberts' 12th problem. So, Samit,
all right. Well, thank you very much for the invitation to speak, and thank you for the very kind introduction. It's really an honor to give this talk. Obviously, I wish I was in person, and I hope to visit someday in person. But it's really a privilege to give the opening talk of this conference, and I really thank you. So I know this is supposed to be a general audience talk, so I'm going to do my best in that regards, and I think there'll be something for everyone, and there will be some more technical slides that are geared towards experts, but they'll be interspersed, and it should be very easy to pick up once those are passed for the non-experts. Okay, so let me begin the talk. Oops, I have to share the screen first. And okay, and now I go slideshow. Okay, so this should be shared screen. Hopefully everyone can see. So my talk is on Stark's conjectures and Hilbert's 12th problem, and I'll describe what each of these are. So today I'm going to discuss two central problems that are connected to one another in number theory. One is that of explicit class field theory, and the other is that of special values of L functions. So explicit class field theory, from kind of a highbrow approach, can be viewed as a refinement of the GL1 case, the Langlands program. But it has more classical roots and underpinnings. So it generalizes the theory of complex multiplication, and it was codified in Hilbert's famous ICM address as the 12th in his famous list of 23 open problems. The second problem or field of study within number theory here that I want to focus on is that of the special values of L functions. And the specific conjectures that I'm interested in are one of the sort of first really open questions in this direction, are some conjectures of Stark stated in the 1970s. And probably the most famous open problem in this direction is the so-called Burson-Swinnerton-Dyer conjecture, which was stated by Tate toward the end of the 1970s. So there are much fancier and more general versions, connected to arbitrary motives called Bailenson's conjectures and integral refinements due to Bloch and Kato. So these are two central problems in number theory, and I want to kind of talk about their relationship. So let me start from a fundamental definition that a complex number is called algebraic if it is the root of a non-zero polynomial with rational coefficients. And a non-trivial theorem that one proves upon learning of the definition of this set is that the set of such numbers actually forms a field. They're closed under addition, multiplication, and division. We would like to understand, as number theorists, the symmetry group of this field, that is the set of automorphisms of this field, which forms a group called the Galois group. And the Langlands program, which is one of the central, most important themes in modern number theory, attempts to understand, takes a representation theory point of view on this question. That is, how do you understand a group? You understand a group through understanding its representations. So the Langlands program tries to understand all the n-dimensional representations of this Galois group, GQ. Okay? And you can be a little bit more general. That is, you can look at its finite index subgroups, which are essentially the Galois groups of finite extensions of Q, which are called number fields. So you might take Q adjoin the square root of 2 or Q adjoin I and ask for all the symmetries that stabilize that subfield. And then those are more general number fields that you want to understand. Excuse me, Galois groups that you want to understand. And so class field theory answers the very first example of this. So the first case of this is, what are all the one-dimensional representations of the Galois group, right? And so understanding the one-dimensional representations of a group is tantamount to understanding the abelianization of that group, because a one-dimensional representation is a homomorphism into the multiplicative group of a field, which is abelian. And so such a character, such a homomorphism, has to factor through the abelianization. So really you're asking, what is the abelianization of this field? And by Galois theory, the abelianization of this field can be viewed as the symmetry group, the group of automorphisms of an extension of F, which is called the maximum abelian extension. It's FAB. So another way of thinking about FAB is you take all finite extensions of your field that are Galois and have abelian Galois group, and you take their union or their compositum, and you get what's called FAB. So that's kind of the question that class field theory aims to answer, which is, what is the Galois group of FAB over F, which is called GFAB. All right, so let me do an example now, because this is important to make sure we have examples so we know what it is we're trying to understand. So when the ground field is the rational numbers, is the simplest case, and you can ask, what is this field QF? What is the union of all the finite extensions of Q that are Galois with the abelian Galois group? And there's a very classical theorem of Kronecker and Weber, which says that QAB is obtained from Q by adjoining all the roots of unity. So if you attach a primitive nth root of unity to the rational numbers, then you get a field that is Galois group, that is Galois, and its Galois group is isomorphic to Z modulo NZ star. That is the group of units in the ring Z mod NZ. Okay, so this is and so that's when you do Galois theory, that's usually the first example of Galois extensions that one sees, is these cyclotomic fields, and they have this Galois, this abelian Galois group. And the famous theorem of Kronecker and Weber is that essentially that's all of the abelian extensions of Q. That is, if you have any finite extension of Q, that's Galois, with a abelian Galois group, then it is contained in one of the cyclotomic fields. So e to the 2 pi I over n, it's contained in Q adjoin e to the 2 pi I over n for some n. And that's a very famous and classical theorem of Kronecker and Weber. Now, class field theory attempts to answer this question or understand these abelian extensions in general. So let's say we start with a number field. So that's the finite extension of Q. So you might think of Q adjoin root 2 or Q adjoin square root of -1, which you usually call I, so Q adjoin I. And you might ask, what is the maximal abelian extension of that? So if I take all the finite extensions of that field that are Galois and have a abelian Galois group, and I put them together, what field do I get? So class field theory gives us some information about that. So what it states is that, okay, that these are enumerated in some way. So for every positive integer n, there's an extension of your ground field, which I'll write f sub n, which has a fancy name. It's called the narrow array class field of conductor n. But they satisfy some nice properties. So first of all, they're nested. So if n divides m, then fn is contained in fm. And they give you all of ffab. That is, ffab is the union of all of these fn's. Okay, so really we want to understand, what are these fn's? Well, class field theory doesn't tell you that. Class field theory doesn't tell you what fn is. But what it tells you is how big fn is, or more precisely, it tells you what the Galois group of fn over f is. And I'm not going to tell you that precisely here on this slide, but I'll tell you some sort of sub-information. So when f1, I'll tell you the Galois group of f1 over f, that's what's called the narrow class group of f, or from an algebraic geometry perspective, it's the narrow Picard group of the ring of integers of f, which I'll define in a moment, the ring of integers. And the Galois group of fn over f1, which is the subgroup of the Galois group of fn over f, is a very explicit and easy to write down group. It's the ring of integers, modulo n, the units in that group, modded out by the image of the group of totally positive units of O. Okay, so I should give an example again when I have these generalities. So when your ground field F is Q, then Qn is just this nth cyclotomic field that I was telling you about, Q adjoin e to the 2 pi I over n. So it's the field that shows up in the Kronecker-Weber theorem. And in this case, the ring of integers is just Z. So what is the ring of integers in general? It's the set of all elements in your field that satisfy not just a polynomial with rational coefficients, but a polynomial with integer coefficients that's monic. Okay, and it turns out, similar to before, that this set has the structure of a ring, not a field anymore, but a ring. Okay, it's a ring contained in F. And you know, if you introduce denominators, you get all of F. That is, if you tensor with Q, this O with Q, then you get all of F. But it's some nice subring. So in the case when F is Q, then this O is just Z, just the ring of integers. And so Z mod n star is just what I mentioned before, the Galois group Z mod n Z star. And the group of totally positive units in Z, of course, Z only has 2 units, plus or minus 1, and there's only one positive unit, plus 1. And so modding out by plus 1 does nothing. So you just get Z mod n Z star. And that's what I told you before, that that was the Galois group of the nth cyclotomic field. So this nice general picture for arbitrary fields F is a generalization of what we saw very explicitly for Q, that these fields Qn sort of enumerate all the abelian extensions. But the question, of course, is not just what is the Galois group of Fn over F, but what is Fn itself, right? And that's the question that explicit class field theory attempts to answer. And it really asks, oops, sorry, went backwards instead of forward. So class theory, as I mentioned, describes the Galois groups of Fn over F, and you take the inverse limit of these, then you get the Galois group of the big Fab over F. So class field theory tells us exactly what this is, and there's a nice description of this as a profinite group in terms of something called the Adels. But the goal of explicit class field theory is not to answer this question, but to say more, which is to construct the field Fab itself, or equivalently each of these fields Fn. Just as we said, Qn is obtained by adjoining e to the 2 pi I over n. How do you get Fn for a general F? And that's the question of explicit class field theory. So Q I keep using as my prototypical example. So QAB is obtained from Q by adjoining the special values of the analytic function e to the 2 pi I over e to the 2 pi I x as x ranges over a special set. In fact, that special set is the field itself, Q. Okay. So this is a very nice way of viewing explicit class field theory for Q as an analytic construction. You take this holomorphic function, e to the 2 pi I x, and you plug in all the rational values for x. If you adjoin those values to the rational field of rational numbers, you get the field we really care about, the field of the maximum abelian extension of Q. So the question is, how do we do this for arbitrary ground fields? Okay. Well, that's not known, but the next case, there's sort of one other case that is classically known, which is that of quadratic imaginary field. So if you take Q adjoin root negative D, where D is a positive integer, there's a very famous theorem of complex multiplication, which says that we know exactly what Fn is. Fn is obtained by adjoining to F the J function of an elliptic curve with complex multiplication by the ring of integers in F, and essentially the torsion points of that elliptic curve, the coordinates of the torsion points. It's a little bit more subtle than that. There's something called a Weber function. But the punchline here is that these are modular functions. The J function and the Weber function is applied to the torsion points of the elliptic curve. These are modular functions. Okay, so it's a whole theory of modular functions, which is very well studied and touches upon many different fields of math, from number theory to representation theory, combinatorics. So this modular function, this J function, plays an important role in this theorem. And what we see is that the exponential function, which was so essential for Q, the e to the 2 pi I x function, is now being replaced by these modular functions, right? The J function, or the coordinates of the torsion points of the curve. These are modular functions. And so that's kind of the answer to the question of explicit class field theory, is that there are special modular functions whose special values generate the maximum abelian extension of quadratic imaginary fields. So we kind of have an answer to explicit class field theory for these specific fields. And classically, these are the only cases that were known. So as I said, in 1900, Gilberts stated in his very famous ICM address in Paris, he stated 23 problems that he viewed as the most important in mathematics. And let me just give some quotes. These are kind of selective quotes. It was a much longer address than this, and I've been a little bit sly in my choice of quotes to help sell my own work. But so the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. Since the realm, so this is the Kronecker-Weber theorem that I mentioned earlier. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So this is the theory of complex multiplication that I gave on the previous slide that he's alluding to here. This wasn't completely known at the time of his speech. The theorem that I gave on the previous slide was actually established later in the 20th century. So, but they kind of knew already, and Kronecker had been working hard on this. He called it his Jugendtraum, his dream of youth, to establish this explicit class field theory for quadratic imaginary number field. So it's kind of known that they kind of mostly had it, or were mostly going to get it. They had these modular functions. They didn't quite have the exact right statement yet, but eventually, it was established. But even at that time, Hilbert was aware that going beyond this quadratic imaginary case is really going to require a substantial new idea. This is really, there's sort of a dividing line here. So finally, the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. So now I want to state some modern perspectives on this, or really a particular perspective due to Stark, arising in the 1970s, which connects special values of L functions, which I'll be talking about for the next chunk of the talk, to the question of explicit class field theory. So throughout the 1970s, Stark stated a series of conjectures proposing the existence of elements in these fields, Fn, that I've discussed, whose absolute values are related to L functions. So you have embedding of Fn into complex numbers, and you take its usual complex absolute value, and he predicts there are special elements whose complex absolute values are certain interesting transcendental numbers that are related to L functions. I mean, the absolute value, the logarithms of the absolute values, I should say, are expected to be sort of transcendental numbers that are related to these L functions. Okay, so Tate made Stark's conjectures more precise, and he stated a kind of more algebraic form of Stark's conjectures, which are called the Brumer-Stark conjecture. And I'll state this conjecture precisely later in the talk because it's kind of the focus of my work recently. Gross refined the Brumer-Stark conjecture using p-adic L functions and stated what is now called the Gross-Stark conjecture, which relates p-adic L functions and p-adic logarithm Stark units. And then throughout the decades since, there's been lots and lots of work on these conjectures. And I just want to point out there's many names I didn't mention here, but Rubin, Burns, and Popescu, and they're higher rank versions of Stark's conjectures that are very important that they stated. And these authors, together with Greither and Kurihara and Sano and many others who I'm not going to mention now, have made some really important progress on Stark's conjectures. And much of this, I should say, builds on Wild's proof of the Iwasawa main conjecture Iwasawa theory, building on his joint work with Maser. And a lot of the recent work has been, in the past decades, has been established by building on the results from Iwasawa theory. So now let me say a little bit more, but still qualitatively, what setting we're working in and what kind of results we have. So let F be a totally real number field. So what that means is that if you take any embedding of the field into the complex numbers, the image actually lands in the real number. So example would be Q adjoin root 2. If you take the rationals adjoin a square root of 2, right, square root of 2 either lands to the square root of 2 or it lands to the negative square root of 2. And both of those embeddings land in the real number. So that's a totally real field. And in this context, the Brumer-Stark conjecture predicts the existence of certain elements in these extension fields Fn, which are called Brumer-Stark units, and they're related to L functions of F in a very specific way, which I'll talk about later. The Gross-Stark conjecture predicts that these units are related to p-adic L functions in a very specific way. So this was a generalization of Brumer-Stark stated by Gross, or I should say a refinement, maybe. So now let me talk about some of my prior work in this area. So I've been thinking about this circle of ideas since my undergraduate thesis, actually. And in my graduate thesis, I stated an exact formula for Brumer-Stark units. So in my undergraduate thesis, I kind of proposed the question of, can one state an exact formula for Stark units? And in my graduate thesis, I proposed a conjecture for an exact formula for Brumer-Stark units. I did it in a very, very special setting in my PhD thesis. And then throughout my postdoctoral tenure and my work after that, when I became a tenure track professor, I continued in the same line of reasoning, working on this for many, many years. And with many of these joint authors that you see here, I came up with more and more refinements for this conjectural exact formula until finally we have like kind of a very general, nice framework for how we can state exact formulas for Brumer-Stark units in all settings. And so that was still a conjecture. So we have a very strong refinement of both, the Brumer-Stark conjecture and the Gross-Stark conjecture to give an exact conjectural formula. But of course, this was all still conjectural at the time. So one of my most significant early works was a proof of the Gross-Stark conjecture in the rank 1 setting due to with Darmon and Pollock. And then together later, much later actually, with Mahesh Kakde and Kevin Ventullo, we figured out the higher rank setting. So this is, relating a determinant of p-adic logarithms of Stark units to leading terms of p-adic L functions. So this was a conjecture of Gross, and we proved it by building on some work of Ribbett and Greenberg and Stevens, and of course, foundational work of Wiles in the main conjecture. Now, the new results that I want to talk, and new is now, I guess, a relative term. So this is, the past year and a half or so, my joint results with Mahesh Kakde, who I pictured on the previous slide. So theorem 1 is that the Brumer-Stark conjecture holds if we invert the prime 2. So I'll state the Brumer-Stark conjecture later and state precisely what I mean by inverting the prime 2. And theorem 2 is that my conjectural exact formula for Brumer-Stark units holds. So this thing that I've been working over many years to state, we proved that this conjecture holds. Okay, so now let me kind of sell the work a little bit and say that if you're very generous, you can view this as a p-adic solution to Hilbert's 12th problem, because Hilbert's 12th problem can be viewed as asking for the construction of this field f(ab) using analytic functions depending only on the field f. One can prove that the Brumer-Stark units, together with explicit, easy to describe other elements, they generate the field f(ab). So my exact formula expresses the Brumer-Stark units as p-adic integrals of analytic functions depending only on f. And so since we've proven the existence of the units in theorem 1 and the exact formula for the units in theorem 2, you can view this as a p-adic solution to Hilbert's 12th problem. We're giving an exact formula through p-adic integrals, p-adic analytic functions that generate the maximum abelian extension of f, which is, at the heart of what Hilbert wanted. Though I have to be honest and say this is not exactly what Hilbert asked for in his famous speech. I kind of gave you excerpts of his speech, but if you look at the parts I cut out, he asked for sort of a complex analytic solution. And he asked very specifically for special values or transformation properties of complex analytic functions, very analogous to what one does with the modular functions. And he expected that, so there'd be sort of complex analytic functions with certain transformation properties whose special values would generate the maximum abelian extensions. And so we don't know how to do that, and it's not even necessarily expected that is possible. But there are conjectures in the complex analytic direction that are much more of the flavor of what Hilbert wanted, and those remain conjectural and wide open. So our work doesn't say anything about those, unfortunately. Okay, so now let me take a step back. I've been getting kind of far ahead of myself and sort of telling you our results without actually telling you what the conjectures are or what these units are. So now I should take a step back and try to define more precisely what these elements are. So first I have to talk about zeta functions. So to define the zeta function of a number field, I have to consider all the ideals of this ring of integers O and take all the non-zero ideals. Any non-zero ideal has the property that the quotient ring is finite. And we call the size of that quotient ring the norm of the ideal. And then from that invariant, you can define what's called the zeta function of the number field, which is the sum over all the non-zero ideals of the reciprocal of the norm to the power s. Okay, and this has an Euler product formula. So you can take the product over all maximal ideals of 1 over 1 minus the norm of the maximal ideal to the power minus s. And you can show that these are the same. This is essentially some unique factorization statement. Just to give you an example, I always go back to the case of Q. The ideals of Z, so O in that case is Z. The ideals of Z are 0, and the ideals generated by the positive integers. So if you throw out 0, then you're just summing over the positive integers 1 over the size of Z mod nz to the s. But what is the size of Z mod nz? It's n. So you just get 1 over n to the s. And of course, that's the very famous Riemann zeta function. So this is a generalization using these other number fields of the classical Riemann zeta function. So for example, for Q adjoin I, well, all the ideals of Q adjoin I are principal. They're of the form m plus ni, where m and n are integers. And the norm of m plus ni is, of course, m squared plus n squared. So you get 1 over m squared plus n squared to the power s. And you sum this over all non-zero pairs, m and n. But now you're supposed to only be summing over ideals rather than pairs. And every ideal is represented 4 times in the form m plus ni because there are 4 units in this ring. 1, minus 1, I, and minus I. So you divide by 4. So that's the example. That's another example of the zeta function of the number field Q adjoin I. And there's a very famous and beautiful theorem due to Dedekind generalizing a calculation of Dirichlet, which he very famously used in his proof of the infinitude of primes in arithmetic progressions, which evaluates the residue of this zeta function at s equals 1. So it turns out it's a simple pole at s equals 1, and you can say exactly what the residue is of that simple pole. Now it turns out that the formula that I gave before converges for real part of s greater than 1, but you can use, there's a functional equation that allows you to give an analytic continuation to the entire complex plane. So it then makes sense to ask what's going on at 0 instead of at 1. And 0 and 1 are actually related. So you can reinterpret the famous Dedekind class number form that s equals 0 rather than s equals 1 in a way that's easier to remember, actually. There's fewer parts of the formula. And it says that there's a 0 of order r, where r is the rank of the unit group of O. And if you look at the leading term normalized in the usual way, where you divide out by r factorial, then you get negative hr over w, where h is the class number of f. I discussed this before, but it was kind of a slightly different class number. It's the narrow class number. This is just what's called the wide class number, the usual class number. R is the regulator of f, which is a very important invariant that I'll discuss in more detail in a second. And w is a very simple invariant of f. It's the number of roots of unity contained in f, right? So r and little r and little w can be defined sort of simultaneously by saying that O star is isomorphic to z to the r cross z mod wz. Sort of you could prove that O star is finally generated, and because it's subgroup with a multiplicative group of a field, this torsion is finite. So it has, I mean, it's cyclic, so it has to be z to the r cross z mod wz. Okay, so let me just do an example. I'm not going to define the regulator in general, but let me just do an example, okay? So it just gives you a sense of the flavor of it. So if f is q adjoint root 2, then the ring of integers O, I just be calling it O, not OF, as I've done this slide. O is just the z bracket root 2. So it's just a plus b root 2, where a and b are integers. And the group of units of that, so the invertible elements under multiplication in this ring, are just the powers of 1 plus root 2, the plus or minus the powers of 1 plus root 2. Okay, so it's generated by two elements, 1 plus root 2 and negative 1. Okay? So little r is 1 and little w is 2. And then it turns out this ring also has class number 1, so h is 1. And the regulator is the log, and this is basically the definition in general, it's the log of this generator of this unit group, 1 plus root 2, the logarithm of this number. And the theorem is that since little r is 1, that the unit group has the zeta function has a simple 0 at s equals 0, and if you look at the value of the derivative, it's just negative log of 1 plus root 2 divided by 2. Okay. And the reason we care about this as number theorists is that we really like local to global principles. That is, like, we like when you can understand, say, an equation by understanding it mod p for every prime p. That's what local means to us. Like, take an equation, reduce it mod p, find all the answers mod p, and then say, can we say something about the original equation over the rational numbers? Right? That's a global, it's rational numbers. Right? In this class, this zeta function is defined locally. That is, I looked at all the prime ideal, the maximal ideals, and I looked at a simple invariant, just the size of the residue field, like O mod P, that's a field, and it's a finite field, like what's its size? And you're packaging that information together for all the maximal ideals into some function, and somehow magically, when then you take that analytic continuation of that function back to s equals 0, it's telling you something about global invariance of the ring, not just prime by prime. It's telling you all these interesting invariants, the class number, the regulator, and the number of roots of unity, and the rank of unit group. They all kind of show up in the formula. And so it's amazing that you get all this information of these 4 different invariants. On the other hand, it's a little bit frustrating because sometimes you want just one of them, like just the class number. And what comes to you is the class number times the regulator. They're kind of fused together. And that can be frustrating. So it's a very interesting and beautiful theorem. And for the context of explicit class field theory, for making connections with explicit class field theory, we want not just the zeta function of one field, but we want to understand an extension field. So these Fn, these fields Fn, we want to understand them through the lens of L functions. So you want it through the lens of zeta functions, excuse me. And so there's a generalization of the zeta functions that inputs a relative extension. So Fn over F, not just one F, or not just one Fn, but just kind of the data of both of them together, and spits out a more general type of function, which is called an L function. And those L functions are the topic of Stark's conjectures. So to define these L functions, one has to recall the Artin map. And the Artin map attaches to each maximal ideal not contained in N a special element in the Galois group of Fn over F which is called the Frobenius element, and I'll denote that by sigma sub p. Okay, and then once you have this Frobenius element, that gives you a method of defining a very natural function, which is a generalization of the zeta function. So we choose a character. So remember I said we really work through the lens of representation theory. So let's take a character of our Galois group. So say just valued in the multiplicative group of the complex numbers. Then you can associate a function which we'll call ln, so keeping the data of our field fn but with the index n. So ln of chi comma s. This is the product over all primes not dividing or not containing n. The exact same Euler factor I had before, 1 over 1 minus norm p to the minus s, except now I've introduced a root of unity, a little alteration here, which is chi of sigma p. So chi evaluated on the Frobenius element associated to this maximal ideal p. Right? So sigma p is an element of G, chi is a character of G. I can apply chi to sigma p and I get some element in C star, which is a root of unity because G is finite. So this is a generalization, okay? And so it's Artin that realized how to define these, and there's actually a slightly better, more refined version, which I'm not giving here, but this is good enough for our purposes. And so for example, let's just do an example. When chi is the trivial character, then chi of sigma p goes away, and you get exactly what I told you for the zeta function, 1 over 1 minus norm p to the minus s. So you just get the zeta function, except the fact that you're restricting to the p's not containing n. So that's a little bit of a refinement. You're just like throwing away some of these finitely many of these factors. There's only finitely many of these p's that contain the integer n. Okay. Now Stark gave a conjectural refinement of the Dedekin's class number formula, the one that I gave you before, that the leading term of the zeta function was related to these interesting variants. The most interesting part was the regulator. Stark conjecture that there should be a generalization of the regulator that works for these relative zeta functions, if you will, the L functions. Okay, so Stark throughout the 70s refining this, and this is like one version of one of the conjectures, which is that there should exist a unit in the ring of integers of the upstairs field. So you're starting with the downstairs field. You know by class field theory that this upstairs field exists, which we call Fn. We don't know what it is. We kind of know how big it is. We know it's Galois group over F. We don't know what the field is. And now Stark is telling you, hey, there exists some special element in that upstairs field. In fact, a unit in that upstairs field, not just in the field, but in the unit group of the field, such that for every character of the Galois group, the derivative of the L function associated to that character at 0, and the formula is very similar to the class number formula. It's a logarithm of the units, but not just logarithm one unit, but you take a linear combination of the logarithms of all the conjugates of the unit by all the Galois elements, sigma, and the linear combination you take is exactly given by the character chi. So this should hold for all chi's. Okay. So, and then, this W in the denominator is something very similar to what we saw in the class number formula. So this is Stark's generalization of the class number formula to L functions. And this is a wide open, deep conjecture that basically no one knows how to prove. A little technical remark, which is for the experts, is that for this formulation, you have to assume a technical condition, which usually holds, and there's a slight modification that holds if this technical condition does not hold. So I'm just going to skip over that. Okay, now I want to make a observation, which is that, let me go back. The number of conjugates here, the number of sigma of u's on the right side, is exactly the size of the group G. Right? So because for each sigma, there's an element sigma of u. So the number of them is the number of elements in G. Okay. And that's also the number of characters chi, right? The size of a group, of a finite group, and the size of its character group are the same. So the number of equations, linear equations I have here is equal to the number of variables, if you view the sigma of u's as variables. So you can solve for them. You can unwind this, and you can get an explicit formula for sigma of u for every sigma. Okay. Now, the question, and this is the question that I raised in my undergraduate thesis, which is, can you propose a formula for sigma itself rather for the absolute value of sigma, right? So Stark's, let me go back one more time. Stark's conjecture is for the absolute value of sigma of u. So in particular, you get the absolute value of u. right? As when sigma is the identity, you get the absolute value of u. Can you give a formula for u and not just the absolute value of u? If I give you a complex number and I tell you its absolute value, there's a whole circle's worth of ambiguity of what that complex number could be. And I mentioned this is important because the presence of the absolute value represents a gap between Stark's conjecture and our understanding of Hilbert's 12th problem. That as if we had an analytic formula for u itself rather than absolute value of u, this would give a way of constructing certain non-trivial elements that are canonical in this field that you're looking for, Fn. So you wanted to construct this field Fn. Stark told you that these special elements u exist in Fn, but he gave you a formula that they satisfy about their absolute values, but didn't tell you what they are. So can you refine it and tell me what u is? That's the question. And there isn't a general satisfactory answer to that, actually. I don't think, no one's stated complete generality, I think, conjecture for this. So there are special cases, so due to Wren and Check, and also to Charlois and Darmon in certain special cases, explicit conjectural formulas for this unit u. And these are beautiful conjectures of Wren and Check and Charlois Darmon, and they're completely wide open. No one has any idea how to prove Stark's conjecture in those cases, let alone these refinements. So I want to now discuss a conjecture that's a little bit more tractable, which is called the Brumer-Stark conjecture. Okay, so for this, we replace essentially this complex embedding, right? We look at these complex absolute values and take their logarithms. We're going to do something different, which is we're going to look at valuations at a prime, right? An evaluation at a prime is a very simple concept. It's like, what's the largest power of the prime that divides a number, right? So the three-adic valuation of 9 is just 2 because 3 squared divides 9. And the three-adic valuation of 18 is also 2 because 3 squared, 2 is the largest power of 3 that divides 18. Okay, so that's a much simpler kind of invariant, the logarithm of the absolute value, which is kind of has a transcendental flavor. This other invariant is just an integer. So this conjecture is stated in a slightly different form by Brumer, actually, even earlier than Stark's work in the late 1960s. He was generalizing a construction of Stickelberger and a theorem of Stickelberger, who looked at Gauss sums and related them to L functions of Q. Again, Q as our base field, our inspiration for source of examples is always there. And Stickelberger, in the case of Q, found some special elements in these QNs, the cyclotomic fields. He found some special elements there called Gauss sums, whose p-adic valuations he could write down a general formula for. And he found that they were related to L functions. So Brumer conjectured that this should hold in general, which is that if given this field Fn, there's a p unit, not a unit, but the unit group where after you inverted p, such that its a valuation, which I denote by ord sub p here, at a prime above p, that again, if you do a Stark-like thing where you take a linear combination weighted by the characters chi, that this should be the L function at 0. Okay, so that's Brumer's conjecture. Now the thing is, and this has to do with the slightly different version that Brumer gave, which is that Tate kind of realized that you could really make this a clean statement by introducing an auxiliary prime q and scaling the L function on the left by this kind of weird looking factor, 1 minus chi of sigma q times norm of q. The reason for that is the right side is a linear combination of integers, or these evaluations, these ord p's, together with roots of unity, these chi inverse of sigma. You want to know that L of chi 0 is integral in this way. That is, it has the property that it is a linear combination of roots of unity and integers. And in general, it's actually not true. So you can't hope to prove this if it's not true. But it is true once you scale it by this weird factor, this 1 minus chi of sigma q times norm of q. And this kind of Tate realized, kind of getting inspiration from some ideas of Stark. So Tate kind of put it all together and called it the Brumer-Stark conjecture. You can see the relationship between the Stark conjecture, which I stated previously, and this one. Instead of logarithms of absolute values, you have these valuations. Instead of derivatives of L functions, you have L functions themselves. So it has a very Stark-like feel. And it was Brumer's conjecture. You go to the Brumer-Stark conjecture, and of course, you should throw Tate's name in there since he's the one who actually stated it. So this is, and of course, Q has to enter the picture once you've thrown it into the conjecture, and the extra condition that U satisfies is that it's 1 modulo all the primes above Q. So this was stated in 1980 by Tate. So again, in I think the late 1800s, Stickelberger proved this thing that's I'm calling conjecture. Proved it in the case where the ground field is Q using the Gauss sums, and Brumer then said, okay, we should generalize this conjecturally. We should generalize this to arbitrary, totally real fields. Stark already was working with these other L functions, or these L functions, from a different perspective, looking at these derivatives and their absolute values of logarithms of absolute values of units, and Tate kind of combine these perspectives into the statement that I gave. So the theorem, now I can state it precisely. I said that we proved the Brumer-Stark conjecture away from 2. I can say a little bit more precisely what I mean by that. So remember, the Brumer-Stark conjecture is that there exists something in OF n bracket 1 over p star that satisfies certain properties. What we can prove is that there's something in OF n bracket 1 over p star tensor C bracket 1/2 that satisfies properties. We have to invert 2, unfortunately. And I'll just say briefly, we're working on the case of 2, and we have some ideas. We can get it when it's a cyclic extension, for example. We know how to prove it. So we have some special cases we can get rid of the Z bracket 1/2. We're working on the general case, and it's really interesting and difficult, that case. I'll just mention in passing that there's a higher rank version of these conjectures due to Rubin, and we've proved this as well once you invert 2. Let me say something about how this is proved a little bit. So this might be a little bit technical now, and I'm running out of time, and I have some other things I want to say, so I won't spend a lot of time on this. But you can cast this theorem from a different perspective, okay, which doesn't talk about units and L functions. And so first you replace the L function with something called a Stickelberger element, which is an element in the integral group ring, such that its image under every character basically gives you the L function that shows up in the Brumer-Stark conjecture. So the fact that there's an element of the complex group ring satisfying this property is automatic, because the complex group ring breaks up into a product indexed by the character. So you can put any complex numbers on the right side, and there would be such an element theta. So the depth of this theorem is that when you do that, the element of the complex group ring that you get actually lives in the integral group, lives in the Z bracket G. So that's a famous theorem of Deline-Rivet, Casco-Nogues. Okay, and now there's a generalization of the class group, which I call class sub Q, which is, well, the usual class group is what? It's the invertible fractional ideals of the ring O, mod out by the principal ideals. Now, if you only mod out by the principal ideals generated by elements that are 1 modulo Q, then you get kind of a bigger group called the Q class group. Okay? And the Brumer-Stark conjecture essentially states that theta annihilates this Q class group. And the way to see that is that if I take the prime ideal above my Gothic P and I apply theta to it, and I say that its class in the class group is trivial, that means that beta to the theta power is principal. That means it's generated by a U that's 1 mod Q. And that U that is 1 mod Q, you can show it satisfies the properties of the Brumer-Stark conjecture. So this is really a new way to, it's just this is nothing deep here. There's just a restatement of the conjecture from a different perspective. But it's a little bit nicer. It's saying there's a certain Galois module, this class group, and you're saying it's annihilated by a specific integral element of the class of the group ring. Okay, so this makes a very algebraic statement, as opposed to Stark's conjecture, which has this logarithms of absolute values. It's very hard to make that into a sort of a purely algebraic statement. So that's like why we can kind of grapple with this conjecture, because we make it purely algebraic and then turn to something about cohomology, and then try to construct Galois cohomology classes using modular forms. So I'll say that to prove that theta lives in the annihilator of the class group, it suffices to do it over ZP for every prime P. And what we prove is that it's in the annihilator for every odd prime P. So that's why P equals 2 is difficult. And we actually prove a refinement. For those of you who know what fitting ideals are, I know this is a nice concept that shows up in algebra a lot. So if there are any algebraists here, we actually show that it's in the fitting ideal of the dual class group. So the Pontryagin dual of the class group is is a not necessarily isomorphic modulo over the integral group ring. It's isomorphic as a group, but not as a modulo over the group ring. And so it might have a slightly different fitting ideal in it. And it took some important ideas of Popescu and Kurihara to realize the statement one wants is that theta lives in the fitting ideal of the dual class group. It doesn't necessarily always live in the fitting ideal of the class group. But the fitting ideal of the dual class group can be shown to be contained in the annihilator of the class group. Okay. So I know I was probably originally scheduled to end at 11:30, but I started a little bit late. So I hope it's, how much time should I take actually? Or should I try to end soon?
You can take 15 more minutes.
Yeah, you can take 15 more minutes or whatever. You have started a bit late, and there's no problem. Whatever.
Okay, I'll try to do better. I'll try to take maybe 10 more minutes.
Yeah.
So
Yeah.
let me say,
Sure.
now, yeah, so I realize the last few slides have been quite technical so for the general audience, let me try to give a diagram here for some of the ideas that show up in the proof of this theorem, okay? So one wants to relate L functions and class groups, and it's a big mystery how to do that before Ribet's work. And Ribet had sort of a spectacular advance in his proof of the converse of Herbrand's theorem. So, the first idea is that modular forms should play a role. So the reason that L functions are related to modular forms is that L functions are the constant terms of Eisenstein's series. Okay, so certain special modular forms, the first examples of modular forms that one ever sees are called Eisenstein series. And so one can realize the L function special values of Eisenstein series. Now from Eisenstein series, you can make cusp forms. Okay, cusp forms are basically modular forms whose values at a certain special point called the cusp infinity are 0. And you can make cusp forms out of Eisenstein series. In fact, the very first cusp form that anyone sees, the delta function, it's defined using Eisenstein series. You take E4 and E6 and you put them in the same weights, take E4 cubed and E6 squared, and then you subtract them once you scale them so that they have the same constant term. You subtract them so that the constant terms cancel, and you get a constant term of 0. And by constant term, I basically mean the value of that modular form at infinity. So you've canceled it off, and you have something that's value 0. And so that's a very special type of modular form called a cusp form. And the reason that cusp forms are important, why did you do this hard work to get a cusp form, is that cusp forms have Galois representations associated with them. So this is homomorphism from the Galois group of Q, or the Galois group of some subfield of Q in a more general context, taking values in sort of GL2 of QP typically, or GL2 of some finite extension of QP. And these Galois representations, when they come from cusp forms that are constructed using Eisenstein series, they have a reducibility property, which allows you to construct Galois cohomology classes out of them. And from these Galois cohomology classes, you can use Kummer theory to relate Galois cohomology to class groups. This is some basic, Galois cohomology. So when you're first doing Galois cohomology, learning about Galois cohomology and number theory, one of the first things you learn is the relationship between Galois cohomology groups and class groups. So this is kind of the complicated circle that Ribet envisioned to relate L functions to class groups, is to go around this circle. And I want to give Barry Mazur credit in his diagram. He gave a very beautiful talk at Ken Ribet's 60th birthday party. 60th birthday conference, I should say. It was a party, but the 60th birthday conference. And I kind of have, and there's a beautiful article in the bulletin of the AMS that he wrote about this, and I've kind of cribbed this this slide from him. Now, I had a few slides here. I wanted to give some technical details, but I think it's really not so important. And I'd rather focus on the last half of the talk, where I talk about Hilbert's 12th problem. So let me talk about that now. So I mentioned this conjecture that I stated, starting from my PhD, lasting through the next kind of 10 to 15 years after I studied conjectural formulas for Stark units. And in very broad strokes, the conjecture has the following form. This unit, which we, Broomer-Stark unit, which was conjectured to exist by Broomer and Stark, and now Mahesh and I have basically proven exists, other than this little annoyance at 2. The conjecture is that that unit has a specific p-adic formula, okay, that it's given by a specific power of p times a p-adic integral. And this is a multiplicative integral in the sense of Henri Darmon. And it's just integral the function x. So where's the content? It's the function x, but with respect to a very interesting measure. And this measure is called the Eisenstein cocycle. And I don't really have time to discuss it in detail. I've given entire talks on just the Eisenstein cocycle. But I'll just say that there's a work of many, many mathematicians to study the Eisenstein cocycle. So Shintani, has an approach to L functions that that people realized had a cohomological feature to it. So David Solomon had some foundational works in this direction. David Solomon, I hope I said, yeah, David Solomon had some ideas, and he worked with Richard Hill. Richard Hill then came up with a very nice clean construction. There are other approaches due to Bailenson, Kings, and Levin. Robert Check has an amazing paper in Inventionis. Glenn Stevens has a modular interpretation, and so more recently, Bergeron, Charleroi, and Garcia have an approach using Eisenstein series on in very general reductive groups. I think they work. So there's a lot of study of this Eisenstein cocycle, and there's a very rich literature which I encourage people to take a look at. But somehow, basically integrating this Eisenstein cocycle in some sense gives you the Broomer-Stark unit. So that was my conjecture. And what's amazing is this conjecture is programmable on a computer. So I actually had 2 undergraduate students here at Duke, I think a sophomore and a junior, and they coded this up. So they wrote code to calculate these p-adic integrals. And it's kind of a fascinating thing to see. So you give the program some real quadratic field, like Q adjoin square root of 305. Okay, so this is an example of a totally real field that we don't have explicit class field theory. It's the simplest kind of example. Real quadratic field, Q adjoin the square root of a positive integer. And you ask it, okay, what's F1? The simplest thing. What's called the narrow Hilbert class field? The F1, the first element of this tower of extensions of F. What is that? And the computer computes all these U's, and it takes their elementary symmetric powers, and these are p-adic numbers. And then you take the elementary symmetric polynomials of these p-adic numbers, and they're horrible p-adic numbers, right, that you get. But then you ask it, these elementary symmetric polynomials, and they're supposed to be integers. And so then it tells you like 9. And then you know that it's right, because if it wasn't, these horrible p-adic integrals, they would just be junk if it wasn't the right answer. So you just get it. So then you're in good shape. And indeed, if you write down this polynomial and you look at the splitting field, it has all the properties that this F1 is supposed to have. It's a Galois extension, it's an abelian Galois group, and it's unramified at every prime. So that's the property that makes this F1 unique. And so you see that you're correct. You got the right field at that point. Okay. And we have proved this conjecture, so we know that the theorem is right. But it's very nice that so you see we're not telling the program the extension F1. We're telling the program just the ground field F, the root 305. That's basically the only information you plug into it. You tell it the number 305, and then you give it some prime p, and I think I used p equals 3 here, and then it computes these units, and then the program spits out the field extension. So that's kind of really solving Hilbert's 12th problem from a, like, if you're generous, it's solving at least, you could say, explicit class field theory, because it's telling you F1 using analytic information intrinsic only to the field F. So I think I have some more examples, and then I'll basically conclude. So I have the bigger example here, 473. So the numbers get bigger. It has a degree 6 extension. So there's a Z mod 6Z Galois group here of this F1. And again, you just plug in and you get these crazy p-adic numbers, but then you combine them and you get these integers. And even though these look large, I mean, compared to the amount of precision, it's nothing. Like, there's 100 p-adic digits of precision, but there's only 6 digits of here. So okay, and so it works again. This is a totally unramified extension of this field. So it's nice. And my students did thousands of examples. So they have thousands and thousands of examples which is on GitHub. If you look at our paper, we link to their website. And getting back to Hilbert's 12th problem, what Mahesh and I prove is that if you take your ground field f, say q join root 305 in the example, and you take not just one u, but all the u's, right, that you can make for all the n's, you have fn for each n. So if you take it for every n, all the u's, then you get the maximum abelian extension of f, as long as you throw in certain special square roots. So square roots are really easy, obviously. So there's certain special elements you have to take the square roots, and once you throw then all of them together with all the u's, you get ff. And remember, I just gave you on the previous slide sort of some evidence that our theorem gives you the u's analytically. So now we've analytically generated the u's. We have these simple square roots. You throw them all together and you get ff. And that was Hilbert's problem, was to construct ff. Of course, he wanted a complex solution, not a p-adic solution. So I'll just conclude as my last slide. That let me just introduce some new features which show up in the proof of this, beyond what we did in the proof of Broomer-Stark, which is that there's an integral version of the Gross-Stark conjecture, which I alluded to early in the talk, which has to do with towers of fields and integral group rings, and that was due to Gross, and the higher rank first due to Popescu, and we prove that's actually what we prove. And then earlier I had proven that higher rank conjecture, or excuse me, not the higher rank, that tower fields conjecture, that implies my conjectural formula. So that's how we actually access the formula. And the method that proof, that latter proof, the implication that Gross's conjecture implies mine, it inputs some ideas from Taylor-Wiles theory, this idea of auxiliary extra primes, and what some people call horizontal Iwasawa theory, this idea of Wiles, that you can sort of fatten something up rather than by going in a vertical p-adic direction, by going horizontally, introducing primes that are 1 modulo high powers of p, and looking at their unit group. Their unit group is highly divisible by p. And so you get more and more p-adic information that way. And this kind of idea was suggested to me when I was a postdoc at Harvard by Richard Taylor. So I'm very thankful to him for that. All right, so I think I'm gonna just end the talk there. Thank you very much for your attention, for coming out so early to hear this. Thank you.
Is there any question from the audience here?